Hey, everybody. Welcome back to my podcast, Anatomy and Physiology Bit by Bit. This is your host, Dr. Steve Sullivan, here for episode 15 of the podcast. You may notice that I sound a little different right now, and that is mainly because I am recording this from my car as I am trying to get these done the best I can while I still maintain all the things I have to maintain during this summer and quarantine time. So I just dropped my son off at a skate park. Today's his 14th birthday, and he's asked if I could take him to a skate park. So I'm sitting in my car and recording this intro while I wait for him to have his fun with his friends. In this episode, we're going to be covering muscle tissue, specifically the histology of skeletal muscle tissue, and what muscle cells or muscle fibers are made up of, so that we can better understand how skeletal muscles contract and perform the functions that they perform. So we are at the end of June right now, 2020. That's when I'm recording this, and hopefully your summer sessions are humming along. If you're taking A&P right now, if not, and you're just listening to learn some more, that's pretty cool too. So up in the northeast of the United States, things are starting to pick back up again, getting some opening of businesses, and the coronavirus pandemic is still going strong in a lot of areas in the U.S. And we might see a little bit of a pullback, but that's basically what happens with an infectious disease. We have a lot of people going back out, and social distancing may not be getting it adhered to the way we would hope, and mask wearing might not be as ubiquitous as we had hoped. So hopefully people will continue to follow the guidelines that are suggested by the epidemiologists and not by politicians, so that we can keep this virus under wraps and get back to as close to normal of a life as we could possibly hope for. So, like I said in a previous episode, we're in one of my favorite topics to teach in A&P, and that is skeletal muscle. Skeletal muscle does so many things. My previous episode talked about all the functions of skeletal muscle, and we got to talk about how they move your skeleton, how they keep your skeleton upright against gravity, how they generate heat so that we can maintain our body temperature. They burn a lot of energy. So skeletal muscles are pretty cool. They're the way we move things around, the way we move our body, the way we can generate force on the world around us. And I think that's a pretty neat system that we have going on to have the available mobility that we have. One of the things I like to teach in my A&P class is that the human body abides by a set of rules, and those rules can apply in so many different cases. I'm going to do a bonus episode, I think, about the 5 rules of the human body and how you can apply those to almost anything you learn in A&P. But one of those rules is move it or lose it. So you've probably heard that phrase, move it or lose it, and muscles are definitely the move it or lose it brand. Um, when you don't use your skeletal muscles, your body is not going to worry about spending the energy required to maintain those muscles. It takes a lot of energy to maintain the proteins that make up your muscles. And if you don't use them, then your body's going to get feedback that it's unnecessary to spend that energy, and muscles will shrink, which we call atrophy. So you may have noticed this yourself if you've been engaged in a workout program where your muscles got larger because you've increased the number and size of skeletal muscle fibers in a whole muscle so that you could generate the kind of force that you've been asking your body to generate. If you stop asking your body to generate that force, then your body will no longer maintain those skeletal muscle proteins that they've built up to generate that force, and your muscles will shrink. Move it or lose it. Think about astronauts who go into an anti-gravity or a zero gravity environment. And they get into a zero gravity environment for an extended period of time, and when they come home, they're weaker. Their muscles have shrunk and they have to work. In fact, many of the astronauts now that you see going into space, they have mechanisms and apparatuses available to them so that they can maintain their muscle mass and their bone mass while they're in a no gravity environment. So move it or lose it is a principle that you can apply to skeletal muscles, especially not just skeletal muscles. Lots of things will apply in terms of move it or lose it. We'll talk about it later on in the endocrine system when we discuss glands and the secretion of hormones and neurotransmitters, and maybe even how it applies to addiction. But with skeletal muscles, move it or lose it is a big one. Another one that I like is the squeaky wheel gets the grease. And that basically is saying where you need a blood supply is where you're going to get your blood to move to. So you only have a finite amount of blood to circulate through your body at any given time. And if you're running a marathon and your leg muscles, the muscles of your lower limbs, are the ones that are really the ones that are in demand right now, and they need the most oxygen, they need to get rid of the most waste products, they need the most glucose, then we're going to expand the arteries that go to the muscles of your lower limb and constrict the arteries that are going to other places that are non-essential at the moment. So we divert our blood supply toward the areas that need it the most. So I like to call that the squeaky wheel gets the grease. So that's a little hint into two of the principles of the 5 principles that I'm going to be bringing up on a bonus episode soon, that are ways that I think you might be able to use those tips and hints to helping you with your course. All right, having said that, I think it's time that we talked in depth about the details of a skeletal muscle cell, which we also call a skeletal muscle fiber. So let's get at it. Skeletal muscle cells, also known as myofibers, have their own unique terminology when it comes to typical cellular structures. The prefix sarco comes from the Greek for flesh. Muscles being fleshy, this prefix is used to refer to muscular structures. For example, the plasma membrane of a skeletal muscle fiber is called the sarcolemma. Instead of a cytoplasm, myofibers have a sarcoplasm. Since each myofiber is a combination of multiple embryonic stem cells called myoblasts, myofibers are multinuclear. This means they each have more than one nucleus. The sarcolemma is a typical plasma membrane, complete with membrane proteins like sodium and potassium ion channels, among others typical to an animal cell. Contracting muscles is a lot of work, and that requires a lot of energy. So as you'd expect, the sarcoplasm has an abundance of mitochondria for synthesizing ATP. But instead of relying solely on the blood for a glucose supply, myofibers store glucose as a starch called glycogen. And since we get the most energy out of glucose when oxygen is present, the sarcoplasm has an oxygen-binding, pigmented protein called myoglobin to make sure there's always a ready supply of oxygen when needed. Most of the space in the sarcoplasm is taken up by the contractile machinery of the myofiber, the myofibrils. The myofibrils consist of multiple protein filaments arranged into contractile units called sarcomeres. The sarcomeres are surrounded by the smooth endoplasmic reticulum of the myofibers, which is called the sarcoplasmic reticulum. The sarcoplasmic reticulum has a mesh-like appearance, with dilated sacs intermittently dispersed throughout. Those sacs are filled with calcium ions, and they're called terminal cisterns. The calcium ions are in much higher concentration inside the sarcoplasmic reticulum and are bound to proteins called calmodulin and calsequestrin. The calcium ion gradient between the cytosol and the inside of the sarcoplasmic reticulum is maintained by primary active transport pumps that pump the calcium ions into the sarcoplasmic reticulum against their concentration gradient. This gradient will be important to understanding some of the steps of muscle contraction. If we examine the myofiber from the inside with a longitudinal section, we would see that the sarcolemma isn't a smooth membranous shell. It has these transcellular invaginations that dive down from the surface and run between two terminal cisterns, all the way to the other side of the myofiber. These invaginations are called transverse tubules, T-tubules for short. One T-tubule and the two terminal cisterns surrounding it combine to form what's called a triad. In addition to the typical sodium and potassium ion channels, the membrane of each transverse tubule also has voltage-sensitive receptors called dihydropyridine receptors, or DHP receptors. These are physically linked to calcium ion release channels in the terminal cisterns that remain closed when the myofiber is at rest. These channels are called ryanodine receptors, or RYR1 receptors. This complex regulates the release of calcium ions into the sarcoplasm, which is imperative for muscle contraction. Most of the space in the sarcoplasm is taken up by the contractile machinery of the myofiber, the myofibrils, which are arranged in units called sarcomeres. The myofibrils of a muscle fiber are comprised of long, thin, parallel structures called myofilaments. There's a thick filament, a thin filament, and an elastic filament that runs inside the thick filament. Each myofilament consists of one or more different proteins. One contractile unit of a muscle cell consists of a series of these myofilaments and is called a sarcomere. The outer boundaries of a sarcomere are called the Z-discs, and the midline of the sarcomere contains a protein complex parallel to the Z-discs called the M-line. The myofilaments are the contractile machinery of the myofiber and are arranged in an alternating pattern of thick, thin, etc. This pattern, along with the alternating regions of overlapping filaments, is what causes the alternating light and dark appearance of a myofiber under the microscope. It's the reason skeletal muscle is also known as striated muscle. The word striation means a series of linear marks. The thick filament is comprised of hundreds of molecules of a protein called myosin. One myosin molecule consists of a head and a tail. The tail is made up of two chains of amino acids that are braided together, while the head consists of two rounded processes projected off the tail at an angle. The tightly bound tails of the myosin tend to cross the middle of the thick filament, while the heads extend laterally, leaving a bare zone in the center. This zone is known as the H-zone, or H-band. The length of the thick filament within one sarcomere is called the A-band, and the region between the end of a thick filament in one sarcomere and the beginning of another in an adjacent sarcomere crossing the Z-disc is called the I-band. The elastic filaments are made of a protein called titin, and that is attached to the Z-discs on either side of a thick filament. It runs through the thick filament to the M-line. By anchoring the thick filament to the Z-disc and the M-line, the elastic filament holds it in its place and helps give muscle tissue its elastic quality. The thin filaments are about half the diameter of the thick filaments, and their main protein is a spherical protein called globular actin, G-actin for short. G-actin molecules are bound to one another end to end to form what is called filamentous, or F-actin, which resembles a string of pearls. Now imagine two strings of pearls twisted around each other, and you have an idea what the thin filament looks like. Each individual molecule of G-actin contains a region that can actively bind with a myosin head. It's called the myosin binding site. It's also known as the active site. When the myofiber is at rest, these binding sites are blocked by another protein called tropomyosin, which is organized like lengths of ribbon wrapped around the intertwined strands of F-actin. Each tropomyosin molecule is bound to another protein called troponin. Troponin binds calcium ions, which is an important feature for muscle contraction.
Bombas makes the most comfortable socks, underwear, and T-shirts.
Warning, Bombas are so absurdly comfortable you may throw out all your other clothes.
Sorry, do we legally have to say that?
No, this is just how I talk, and I really love my Bombas.
They do feel that good. And they do good, too. One item purchased equals one item donated.
To feel good and do good, go to Bombas.com and use code AUDIO for 20% off your first purchase. That's BOMBAS.com and use code AUDIO at checkout.
The thin filaments are anchored to the Z disc via a protein called alpha-actinin. The thin filaments are also bound to a protein in the sarcoplasm called dystrophin. Dystrophin is then linked to the sarcolemma, making sure that when the sarcomere contracts, the rest of the muscle does as well as dystrophin tugs on the sarcolemma. Since myosin and actin are directly involved in the contraction of the sarcomere, they're considered contractile proteins. Tropomyosin and troponin are the proteins that regulate when the sarcomere can contract, so they're called regulatory proteins. So there you go. That is a pretty in-depth look at the cellular structure of a skeletal muscle fiber, or a myofiber. This is going to be really important for you to retain as you try to understand how muscle fibers are excited by neurons, how they conduct that excitation to the appropriate structures, and how the muscle fiber contracts or gets shorter so that muscles can actually move the skeleton, or even just hold the skeleton still. And in some cases, not move the skeleton at all, like move your lips around or open and close your eyes. So from my episode 14, you might remember that sometimes when skeletal muscles contract, they don't move the skeleton. So there's a lot to remember. It's an important thing to look at. Hopefully you've got some images that will help you along with this cellular anatomy that can help you to understand the next step. And in our next episode, I am going to go from excitation all the way to contraction. That's 3 phases in which muscle cells, skeletal muscle cells, can shorten or contract. So stay tuned for episode 16 so you can fully understand the way they do that. All right, enjoy the rest of your day. Good luck on your next exam. Talk to you next time. Hey everyone, don't forget to check out my YouTube channel, Student Help for AP. Student Help, the number 4, AP. There's a lot of tutor videos on there that I think could be really helpful. I also have an Instagram account and a Twitter feed with the same name. Anatomy and Physiology Bit by Bit is a production of Minus 55 Media, with a special thanks to Bucks County Community College, McGraw-Hill Higher Education, and my family.